Sorry, just a second. Yeah, I'm sorry. I have some network issues today. Hello. Yes, I'm sorry. I have some network issues today. Unfortunately, I'll try to navigate through them. Um, right. Okay, thank you. So I'll just give a brief recap again since this was really disturbing. The concept that we are looking at today is the concept of modified wave number. So any general periodic function can be represented by ck e raised to power I k x. So this is something that we've learned in our complex numbers as well, that e raised to power I k x can be represented as cos kx, that is cos theta, minus iota sine kx. So over here at theta is kx. So k is the wave number for that. Okay. So then our ux looks something like this, what you can see on the screen already. And then the exact derivative, that is when you take the derivative of it analytically, and the derivative of ux, then you get something like iota k ck e raised to the power I kx. Okay, so you can identify over here that the the term that is ux, which we saw over here, is being repeated in the derivative of dux. Okay, so this is true for periodic functions only. This is a work that we're doing for periodic functions only, because it's not going to be true always. Okay, and then what we do is that we break down whatever our expression for the exact derivative we have in terms of ux and the wave number k as well as iota, which we will be able to get from simply, if you look at this, if you do this derivation on your own, that is just this differentiation, you will be able to see that. So now we are looking at a certain grid point which is at j, which is at index j. So then this index j, like for example, if we were looking at 1 2 3 indices in this particular mesh, then, and we know that delta x is equal to uh, 1 meter, for example, we know that. Okay, then what happens, that we can easily get to know that our x at j is equals to j into delta x, that is 2 meters, right? I would say 2 into delta x, which is 1 meter. This is 2 meter. So then I'm just going to look at any arbitrary grid point j. Why we are talking about grid points is that we are dealing with CFD, and inherently that means dealing with a discrete mesh. Okay. Then we compute the derivative using one of the schemes that we have already learned. So here the schemes would be such that whatever finite difference schemes we have looked at, for example, central differencing, right, central difference or forward difference, right? And in the last whatever week's classes, you must have heard of the schemes part A, CD, part A, fourth order, as well as CD4. So these are some of the schemes that you have already seen in the classes. Then after getting the derivative, we put it in the form of iota kx ujx. Okay, because over here this is the same form that we discussed earlier. That is this form given by the equation number 1. Okay, so we just compare both the forms. Okay, so over here we have a different wave number. We are not going to say that we're going to have k exactly. We're going to have something like k star, right? So this is my modified wave number. Why am I calling it my modified wave number? Because after whatever operations that I have done, I have been able to get a form that is similar to my equation 1, and in that I am trying to compare what k looks like when I'm using the modified equation for finding out my derivative. Okay, so then we match it with the standard form given by 1, and over here we have ikx equals to, it's not necessarily equal to, but we are going to compare it. Let's just say versus. So over here we are able to see that okay, k and k star are analogous, therefore k star is known as wave number. K and k star are analogous. Okay, so this is basically the approach, that basically we are just trying to put our derivative that we get from the various equations and all that we have used, and we try to match it with the standard form of the derivative, and therefore we are able to get a modified wave number for periodic functions only. This is applicable for periodic functions only. Okay, fine, right. So then moving on to the first question that I have over here. The modified wave number method assesses how well a finite difference scheme can differentiate dash functions. So we want to look at a certain type of function. Okay, Linishi C. Does anyone disagree with this? Great, Apurva. Sinusoidal is periodic, therefore fine. C. So everyone is unanimous over here that we have sinusoidal since it is periodic. Great. Okay. So we'll move on to the question number 2. We have an illustration over here which I've already done so that we're able to understand the question better. Let's read. A uniform grid is formed when a domain of length 1 meter is discretized into 20 equal parts. This grid is used to accommodate 20 wavelengths of a sinusoidal function. What is the value of wave number? We want the actual wave number, that is we want the k. Okay, over here we are being asked k. And what will be the maximum possible wave number to be accommodated by in this grid? Okay, what is the maximum possible wave number? Fine. So first question that I will ask is that okay, I have over here, I'm going to draw a sinusoidal wave. This is sinusoidal wave over here, and this is half of a sinusoidal wave over here that is under this. So then answer in this term that from A and B, which length, A length or B length, which length is the wavelength? A is the wavelength, everyone is agreeing with that. Fine, so that's the correct answer. So A is the wavelength. So what I'm being told over here is that this is 1 meter, whatever this entire long box you are able to see, that is sorry, did I get a notification? Okay, no, fine. So we look at what is happening over here in detail. Okay, so then this entire thing is 1 meter, and I've maximized it so that we are able to see what is happening. So what is happening is it told me that in this 20, there are 20 boxes in my 1 meter, and I have accommodated 20 wavelengths in that. Okay, so then basically, since you all told that one wavelength is equal to the both the halves of the sinusoidal graph, so that means what I have over here is that one wavelength is fitted inside one box. Okay, so this is not great for me. Why is this not great for me? It's because I can only perceive the information at these grid points. Okay, so it's telling me that yeah, okay, your answer is going to be let me just use a brighter pen. Right. So it's telling me that yeah, okay, that your answer is going to be 0 at the grid ends, which is true, but then it's not giving me the correct amplitude. Okay, I'm not getting the correct amplitude over here. If I were to like sort of average out the whatever I have inside one cell, I will get that the value of this sinusoidal function in this cell is 0. Do you understand why? Because I have information only on these discrete points. So if I wanted an information which is not lying on either of these points, what I'll do, the first approach that I'll take is that I will average out my answers which I have from either of these points. But since I have 0 over here, okay, 0 over here as you can read in the graph. So then if I average out 0 plus 0 by 2, I'm going to get 0. Okay, which is okay for this case because again this is lying over here, but then is it 0 throughout this cell? No, right? It's not 0 throughout this cell. So it's not giving me the right information for this entire cell. So basically I can never ever know what my amplitude is going to be by using this formula, because of course I'll get the correct value at the ends. I'm going to get the correct value at the middle because of the nature of the periodic wave of periodic sinusoidal wave. But I'll never get to know that there are amplitudes over here. So according to this grid, this function that I have over here, sinusoidal function, is equivalent to a constant function which is at 0. Okay, let me just represent this on the graph itself. Let's pick a different color. Basically the point I'm trying to make is that for this grid it is blind to my amplitudes. So therefore for this grid, whether I'm putting a sinusoidal curve which you can see in red, or whether I'm putting a constant zero value curve in this box, it's going to give me the same result. It cannot see anything that is inside the box. It can only see whatever is at the extremes, at whatever is at the grid points. Okay, so this is not great for me. Okay, because I need to be able to perceive this information. If I'm not able to perceive this information, it is effectively useless for me to consider this grid. Okay, so this was the point I was trying to make. We'll just get rid of this image. Right. Huh. Fine. So this was an important point, that basically if you're looking at a periodic wave, the amount of boxes that it should occupy should not be like one entire wavelength should not be accommodated in one box. It should be accommodated in two boxes. Okay. This is how I want. Otherwise I will not be able to perceive anything on it. Like I'll just get a wrong answer every time. Then fine. So then what is it asking me? What is the value of the wave number for this case? So what is the wave number for this case? So wave number is given by 2 pi by the length. Okay. 2 pi by the wavelength. So what is the wavelength for this question? It's equal to 1 by 20. Okay. So therefore my wave number is going to be 40 pi. Now let's look at what is the maximum number of what is the maximum possible wave number accommodated in this grid. So we sort of came up with the conclusion that each wave, like instead of this red wave, what we should have is this sort of a blue wave, okay, that we can see over here. So this would be appropriate. Just a sec. So this would be appropriate for this grid, right? Yes, you'll get a recording of this session, Tushar. Right. I'm sorry, I'm having some internet connectivity issues today, so it's not as clear. Hopefully, I'll be able to make the best of it. Anyway, so the maximum wave number that can be calculated is half of this, that is 20 pi. A proper formula to do this is that 2 delta x is the shortest wavelength that can be accommodated So whatever qualitative explanation I gave yesterday, I'm saying yesterday, just before, is something that is mostly just that qualitative. So what we are referring to over in this entire exercise is about the derivative. So the derivative is the more important consideration. Anyway, so then this is like a rule of thumb that you can remember for solving your assignments, that the shortest wavelength that can be accommodated on a grid is 2 delta x. So over here, what was delta x? Delta x was, let's see, What is delta x? 1 by 20, because 1 meter divided by 20 halves, right? So then 2 times of that is what? 2 delta x is 1 by 10, and then I substitute this wavelength value back in my wave number formula, that is 1 by 10, and from here I got the 20 pi answer which I gave you earlier. Okay, then let's move on to the next question, that is what is the Euler formula. So we discussed the Euler formula earlier. Here capital I is used for iota, that we generally know as iota, that is minus. Okay, great. A and D, you are right, Akshat. Okay, so here capital I is used everywhere because we are using I as the index number as well. I'll try to avoid that for confusion. Mostly what I will use is that I'll use J for the index so that we don't run into this confusion at all. Okay, J index and iota. Since I've already started with the iota as the index number, sorry, j iota as the I as iota, therefore I'll not confuse you more, and basically my I will be iota. Anyway, what is Euler formula over here? So we have e raised to the power iota kx equals to cos kx plus iota sine kx. Now let's look at option number D, which Akshata said. So in option number D, what I'm getting is that my theta sorts is equals to minus of minus kx. So in that case, what I'm going to get, e raised to the power minus kx is equal to cos of minus kx plus iota of sine minus kx. Now we all know that cos of minus theta is cos theta, so therefore this will become that, and sine of minus theta is minus sine theta, therefore we come up with option D. So this here we are able to see option D, here we are able to see option A, therefore A and D are correct, right? Okay, then modified wave number can indicate the following errors: amplitude error, phase error, truncation error, all of the above. What is your opinion on this? Okay, so no, none of you have got the correct answer, which is B. Actually, A is also a part of the correct answer. See, basically what we were doing is modified wave number, as we're able to see. What is wave number? Wave number is essentially a marker of the wavelength, right? Wave number we saw was. So this looks very similar to what? No, option C is not right, Tushar. So this is what? Wave number is comparable to frequency. Okay, so frequency is something that is related to phase, and therefore phase error is a part of that, and amplitude error. So for this I would recommend that you go through the lectures once again, because it's not too super easy for me to explain it all over here, but for your reference, this you will be able to find in, I think, lecture 13 or 14, so you can go through that. So this is something you should remember, and if you have a similar question in your worksheet, then we'll be able to look at it. Anyway, I'm sorry I'm a bit short in time today, but then if we want a better explanation for this, we'll have it. We'll have a discussion on it next time. Sorry. Sorry, I have very bad. Hi, sorry, I hope you can see the screen again. Anyway, the modified number can indicate the following errors, that is amplitude and phase error. We will have a better discussion on this next time, even I have need some clarity on it. So I'll be able to explain it to you better the next time around. Sorry for the delay. Anyway, let's look at some numerical questions which are going to be more illustrative of whatever you have already gone through over the week. So let's see what the question is asking us. What is the value of modified wave number for first derivative using CD4 scheme for wave number k equals to pi by 4, which is equal to this value, and step size 1 meter. So let's see what the question is already telling us. It is telling us delta x is 1 meter. It is telling me k, that is my actual wave number, not my modified wave number. It is my actual wave number, that is pi by 4. And it's asking me to use the scheme which is given by CD4. So if you remember the CD4 scheme, which you must have gone through over the course of the week, that gives me the first derivative as this. Let's just write it in terms of u. Oh, I'm not audible, is it?
I'm audible. You are audible.
Okay, I am. Okay, thank you. Okay, right. I hope I'm audible. I'm going to continue. If I'm not, then please again write in the text box. Right. So in this case, CD4 for like a grid point at J is given by U J minus 2 minus 8 U J minus 1 plus 8 U J plus 1. So this is just another scheme which is actually order. In this the error of the order is of this much. Okay. So like we saw the last time, we were looking at the orders of the error for the central difference and forward difference, etc. So we found out that the order of difference for the forward and backward difference was around delta x, and for central difference it was delta x square. So basically it is just the biggest term in your truncation error from the Taylor series. This we already know. Right. So this is what my CD4 looks like. Okay, this is CD4. Let me just outline it for you. Scheme CD4. Right. Okay. So in this case, so there is like basically what our objective is going to be, how we are going to get to the final modified wave number is that we are going to put this in terms of uj, like whatever uj minus 2, uj minus 1, etc., etc. I'm getting. I'm going to try to resolve it and get like a sort of a form of some constant over here, minus some constant C2 uj. Basically my entire idea is to transform into some iota into k star. Okay, this is my modified wave number. Okay, into uj. Okay, this is my entire idea, this is what I want to do. Okay, so then this is a large derivation that you have to do, and how you're going to go about with the derivation is, I'm not going to do the entire derivation over here because that's already been done in the classes before. Sir has derived it for you. So essentially what you do is that you're just going to be like, okay, let's see what my uk is going to be. I know that it's going to be e raised to the power I into k delta. What I want over here is j delta x, k into j delta x. Okay, why j delta x? Because that is my x. So over here my j is minus 2. Like what I'm going to do is that minus 2 delta x into uj. Okay, how am I getting this? Is that I'm going to be like e raised to the power iota k j delta x. So this is minus 2, j minus 2. So from your exponents, you know that it's going to look like a into j minus 2 delta x. Okay. So everyone agrees with this. This is just simple exponent mathematics that we take care of. So our idea is to sort of use these manipulations in order to get this value for the modified wave number. So when we do all of that manipulations, we essentially just break down our uj and uj minus 2, uj minus 1 in terms of exponents and uj. Okay, then we're able to get something uh, something like this for the expression for k star. So this is something that is a standard result. You might have to derive it. And I'm sorry, Tushar. I think others can hear me. Can others hear me?
Yes, ma'am.
Tushar, okay. Everyone else can hear me. Okay, I'll just check. Okay. Right. Sorry. Yeah. It's okay. Sorry for the interruption. So this is the K star that you get. Okay. Can you little bit stuck, ma'am, in terms of what the voice? I'm sorry, I have a bad network today. I'm trying to mitigate that, but yeah, I'm sorry. There is very little I can do today about that. Anyway, from my end, I will be uploading a video of whatever I've said today, and all of this PDF is going to be available on the same places as before. So that should be a good thing. So basically, this is the formula for modified wave number over here, K star, right? So can you just compute it for me? Over here, delta x is 1 meter, like we saw. K is pi by 4, and yeah, so these are the only two things that you need to know. So the Dibyendo is already calculated. He's saying 0.76. Okay, so we go for an answer for 0.76. Let's see where it is. So actually, the answer that I got as well is from this is 0.776. Yeah, thank you, Purva. The same. So we are able to compute this. Okay, so as for how do you get this modified, as for how to get this modified wave number, essentially what you need to do is that you just need to resolve your j minus 2, j minus 1, uj plus 1 and uj plus 2 in terms of uj and iota. So whatever is left, everything else that is left inside is going to be k star. Okay. So the approach is basically whatever I explained in the beginning of class. What you do is that you take your periodic function, which is an exponential sort of a function. You differentiate it analytically. Then you're able to find where your wave number you'll be able to see your wave number in the derivative itself in the form of iota k u j. This is what you get. So you are able to identify that this is your wave number. And now that you know that how to get to your wave number, you what you'll do is that you from a using a similar approach, you will calculate the du by dx again and again, right? Using your different schemes, and then whatever is left, then you resolve your function such that you are able to get I something like this, and you compare it. So it's very simple in that respect. Essentially, what we are able to get is that we see that the wave number is different. That is the frequency that we are perceiving because of a certain grid is going to be different. That is the idea. Okay, because wave number, um, because that's how wave number looks like. Okay, wave number and frequency are related in this that respect. Okay. So then which option is correct for the following statements? Higher formal accuracy scheme performs more superiorly at high wave numbers. Lower formal accuracy scheme deviates more from the exact solution at high wave numbers. So what is your opinion on that? Before you write your answers in the chat box, I'll draw a little graph for you, which you've already seen in your class. Is this? If we have an exact solution over here, this is exact. Okay, this is lower accuracy. Correct. D. D is right. Right. Okay. D is right. You are right. Logesh, I'm sorry you're having difficulty with that. Can you mail me regarding all of your queries? We can talk later, or maybe even after the class, you can stay for a bit. High accuracy, and this is low accuracy. Okay, over here formal accuracy, you're saying this term formal accuracy is right over here. The formal accuracy is just about how what your order of error looks like. Order of error, if it looks like x squares, and then that is lower than sorry, that is lower accuracy. Let me just write it in the words. Lower accuracy. Why we are using the word formal is because accuracy comes in many ways and forms, because your computer is also going to add some error and there are multiple forms of error. But for formal accuracy means that mathematically what error is being introduced. Lower formal accuracy than order of x4. You see, because because delta x is something that is small. Okay, so if you're going to raise it to a power, it's going to become even smaller. The error order. Okay, so therefore, the more the power of the delta x on the order of the error, the lower the error is going to be. Okay, so we're going to say that okay, delta x can be 1 meter as we saw over there. Then what does that mean? Basically, these orders are related to like our Taylor series. Okay, and in that we implicitly assume that it is a very small fraction. Fraction is something that doesn't really make its appearance in terms of any of our equations over there. But then the thing is that if your domain is very big, like if your domain is 200 meters, then taking a delta x of 1 meter is not a bad approximation. Okay, because your order of error is going to decrease as you're going to keep a smaller and smaller grid, because you're essentially, it's like a sieve, right? So if you're having a sieve and you keep on decreasing the aperture of the sieve, you're going to retain a lot more data and let out a lot less air. Okay, so this is what the graph that you saw. Anyway, all of you have already evaluated the answer for this, and that is D. Okay, D is right. What is the value of modified wave number for first derivative for fourth order central difference scheme? Let's have a look at that. So fourth order central difference, this is we're talking about part A scheme, and K is this. So let's again see what all information we have. We have K equals to pi by 4, delta X equals to 1 meter. Okay, so let's see what this scheme looks like. In this respect, again we are what is our aim ultimately? It is to find the derivative, the first derivative. Okay, because we're talking about first derivative throughout this thing. So this is what the scheme looks like. This is formula for the scheme, so to speak. And in this again, you're going to repeat the same exercise that I talked about before. That you're going to resolve it in terms of e raised to the power um, iota kx. Why you're going to do that? Because that is equal to your uj. Okay, and then basically you're going to resolve this entire thing such that you're able to, whatever steps you do, such that you get something like iota k uj. So you don't need to do this for each and every problem. Okay, what you need to know is that k star, modified wave number. I would still suggest that at least once you go through this derivations, either in terms of the lectures that sir has provided, or by your own hand. So that will give you a more clarity regarding why the modified number wave number is looking the way it is looking. But it's a fairly long derivation. So we We cannot cover it in the tutorial session. Essentially, this is how you will solve the problems in your worksheet. So I'm just going to write it down for you. This is what the K star looks like for the Padei scheme. Okay. Can you compute it for me? Delta x equals to 1. Why? How did we get that? We got it from here. Step size equals to 1 meter. And K is delta is pi by 4. Can you compute what you're getting for K star? Okay, great Apurva. Thank you. 0.783. Let's see if that is the question, that's in the answers. So it's close. 0.783, you've truncated it at 3, but it goes on to 0.736. Let's just write it down. 0.783611 is what we get. So that is approximately equal to 0.784. So we are going with that answer. Okay. So, so the nature of this topic that we are discussing today, modified wave number, it is a bit confusing. I'm done with the questions as such because, to be fair, the concept is harder than your worksheet is going to be. But we want to get a hang of the concept as well. The concept is exactly what I've mentioned up top over here, is that any general periodic function can be represented by ck es bar iota kx. This is something we know already. And what we are striving to do is that we are trying to draw a comparison between the du by dx, that is the first derivative that we get analytically, and we're trying to compare that with the derivatives, the first derivatives that we get from all of the different schemes that we have. Okay, so once we do that, we get a value for k, that is the modified wave number, and we are able to sort of get a physical feel of what we are trying to represent versus what we are getting. So in the two numerical questions, which I think were more clear than the rest of the questions, the k is equals to pi by 4. So pi by 4 is around 0.785. So you see that when we are using this Padei scheme, Dibendu, no, I'll not be doing that. That is in the lectures already. The derivation for modified K. That is good. That is clearly given in the lectures. So I suggest you go through that material because that will be a lot more clear than my PDF. Okay. So fine. So then what we saw that for the same problem, this is essentially the same problem. Our step size was 1, our k was pi by 4. So we got from the Padei scheme 0.783611. Okay, which is a pretty good value. It's pretty close to 0.785. So essentially what I have is that I have a wave which is wave number is pi by 4, and I was able to get something that looks like approximately like pi by 4 in terms of the modified wave number. That is, this is a better approximation than what we would get from our other scheme, that is CD4. So in CD4, the K star looks like, what did we compute? 0.776, right? So 0.776 is farther off from 0.785. Therefore, I am able to say that since I know my actual wave number, so then I am able to say that, okay, this scheme, that is the Padei scheme, looks much better than my CD4 scheme. Okay, so this is basically going to help you sort of get an idea of which scheme is going to be better for your functions. Once again, this is also a good question over here, that we have a qualitative question with respect to the arguments that we made. So essentially I stated about the magnitudes only, right? Only matrix equations have been taught. I'm sorry, Dibendu. It's there in the lectures. I've gone through them. In lectures 15, 16, that's around where modified wave number has been discussed in detail. And I've told you the methodology. Essentially, you don't need to be confused about what that is. What we are doing is that going with something similar to what we were doing with the partial differential equations. Basically, what we do is that we get a general form. Okay, so we know what means what in general form, and then we derive whatever we want to in terms of something that looks similar to our general form. So once we have two things that look kind of similar, we are able to draw an equality. We say that okay, that means that this thing is the placeholder for my wave number. K star is my placeholder for wave number, and then I get an expression, and then I just substitute whatever I have over here. Okay, so yeah, so that is the approach for modified wave number, and it is only a way for us to evaluate whether a scheme is better or worse than the other. Okay, so as for the modified wave number, which of the errors it's able to is able to tell, we are able to sort of see by whatever we did in terms of our questions, that it is first of all giving us some information about frequency. Frequency is related with phase, because essentially what we are doing over here is that if our frequencies are different, okay, then they are out of phase, so we are getting some information about phase. Therefore phase error is over there. And since ck since this k that we have over here is also related to the magnitude of the function, therefore amplitude error is also there. Why it's not giving us information about truncation error? Because truncation error is something the information about truncation error we get from Taylor series. Okay, because we leave out certain terms. Okay, we leave out certain, when we are taking the Taylor series, we leave out certain terms which are of the order of 0 this or this or something, right? So then once we do that, we are able to conclusively say that okay, this is the truncation error because we just truncated of certain terms. So that is why it's not giving us truncation error. Therefore it's giving us errors that are related with the wave structure, that is amplitude and phase. So okay, right. Hopefully it is somewhat clear. It is a concept that you might have to revisit in your lectures as well, but essentially the crux of it is whatever I've written in these first two pages. So this is something that if you follow, then you will not be very confused about it, and there is no need to be confused. It's only a way for you to evaluate whether a certain scheme is good for your periodic function or not. Okay, so I will be ending this class now. If you have any questions, then you can ask. But I'm running short on time. I'm so sorry today. Okay, so I'll be here for like around 3-4 minutes more, but you can leave the class if you want to. Apurva, I cannot help you with the actual assignments. I'm sorry. You can write a mail to the professor since we are not allowed to discuss actual assignment questions. Thank you. If this is not a proper question, you don't have to worry about it. You can just write down your observations. It shouldn't be a big issue, because some of the answers can be wrong. So it's not an issue if you genuinely feel that the answer is wrong or something.
Ma'am,
Yeah.
sir, I have a question on Taylor table method. Can I ask?
I will not be able to answer it as of now, since I'll have to revisit that topic once again. Why don't you write a mail to the other TA because he was looking at that subject? Is that okay?
Can I ask in forum?
Yes, of course you can.
Okay, ma'am. Thank you.
Okay, thank you. I'm now ending the class. Logesh, what exactly are your questions? Can you, if you want to, you can discuss with me right now.
Ma'am, I can't able to understand the single class, ma'am. I don't able to understand,
Are
ma'am.
you going through the material that the professor has made, Professor Arnab Roy, that you get a mail for that the you get a mail like the certain material has been uploaded, right?
No, ma'am. No, ma'am.
Yes, you do. If you are coming to this class, you do. How did you get this link for this class?
Yeah, from NPTL I registered, ma'am.
So
I
NPTL
enroll a
NPTL is
Yes, ma'am.
also sending you links of the material that Professor Arnab Roy. You know Professor Arnab Roy? Have you attended a single class of that? Have you seen a single
I
video?
Yes, ma'am. There's one class I saw. And I remember.
Until and unless you see all the classes, there is going to be no advantage of sitting in these tutorial sessions. Why? Because we are relying on the fact that you've already gone through that material. Okay, so actually you should know the material better than we are currently. Okay, because we are doing it from my memory, but you are supposed to do it properly after having gone through 5 hours of material. So until unless you go through that material, you will not be able to understand or follow what is going on this class. I'm still trying to at least write down notes for whatever we'll be discussing, but this will not be enough if you have to clear the course. Okay, Logesh, you have to go through that material.
Ma'am, did you have that material, ma'am?
I don't have that material. That material is on the website, or it's also on YouTube. Let me give you a YouTube link of the uh, intro to CFD.
I
Let,
didn't understand. It is totally it will be different, ma'am. I think it was a difficult course. I think it's.
that's fine, but it's not that difficult. We are there to help you out with this stuff. But then the thing is that you have to go through the proper material first. Whatever
Ma'am,
these
in book stationery it will be available, ma'am. This
No,
for this book.
stationery it will not be available. I'll send you one YouTube link. Okay, wait for a minute. I'll send you one YouTube link, and you follow that. If you're still not able to understand, write to NPTL. Okay, write to NPTL.
Okay, ma'am.
You are using mail, right? Gmail,
Yes, ma'am. Gmail I will use.
right? So you're getting these mails from online courses NPTL now.
Yes, ma'am. In
No,
college mail.
so you are getting those mails, or who's getting those mails?
No, ma'am. I am 18 main man, but material that sir I asked, ma'am, whether he's uploading the recording videos and all,
Yes, I
ma'am,
am
to the
also
mail.
uploading my material, but then you
Okay,
need
ma'am.
to go through the material which the Professor Arnab Rao from IIT Kharagpur, he is putting. Just a second, just give me a.
Just last time I attended only for 15 minutes and then I got meeting and I left the class, ma'am. But I said to him, but he said I'll send you I'll give the material to and I'll send it to you through the mail like that. Sarah said, ma'am. But still now he has
Okay,
meeting. I
this I
didn't
am
got,
putting
ma'am.
a link in the chat box right now. Okay, go to this link right now.
Ma'am, can you
Please go
share
through
your
this
contact,
link.
ma'am?
My contact is already shared. Lokesh, you are not paying attention on the resources, then you will not be able to find out, you will not be able to learn effectively. Go to this link that I've sent you in the chat box right now. Open?
Ma'am, okay, ma'am.
Did you open it?
Okay, ma'am. I open it.
So then what is over there?
Ma'am, and then you can share the WhatsApp contact, ma'am. But
No, I
if I
cannot.
have
I
any
will
doubt,
not be
ma'am,
sharing the WhatsApp contact because I'll send you my email. Write me an email, whatever resources you need, just share. Just
my sir, I asked, ma'am, but he said
which
to, uh,
who is your sir?
I think Arul sir, ma'am,
Who's Arun sir? Where from which college?
in Soyaram College, ma'am.
So then he is referring you to this stuff.
Yes, ma'am. I said to him, ma'am, I have doubts, sir, like that, ma'am. But if you have, if I have, he said, what where you have doubt, come on and ask that, ma'am. But I can't. It is totally the numericals are different, ma'am. That's why, ma'am.
So you have difficulty in the assignments, or do you have difficulty in understanding the lectures? Because I don't think you have gone through the lectures.
I have difficulty in lectures, ma'am. That's why.
Okay, just a second. Uh, you have received the email from NPTEL. I'm sorry, it's just a second. Introduction to CFD, right?
Yes,
So
ma'am.
you're
Yes, ma'am.
attending these introduction to CFD classes or not? Like, are you having a look at those things or not? The videos.
Little bit, ma'am. But I know it is too hard to learn, ma'am.
I would suggest you go through it once again, because if it's too hard to learn, then you have to ask correct questions. Until unless you ask some definite questions, we cannot help you. Right? You are saying it's too difficult. I don't know how to help you with that, right? You have to give me exact question that, okay, ma'am, this is the question that I have looked at and I could not understand this. This particular topic I could not understand. If you could not understand anything, then I would suggest you repeat the course once again. Okay? If that is what is required, because it is we'll be able to only help you if you follow all the material. Okay? I'm sorry, I
Ma'am,
think
can you share your notes, ma'am? What?
my notes are already being shared. Do you have access to that link?
No, ma'am, if it is going, ma'am, but in browser it was to come in, it was secure. What the drive is secured.
So
Like give the request to the browser like that. It was coming, ma'am. That's why, ma'am.
I, I have given the, okay, this is the address from my drive. I'll check whether it's secure or not. I do not think it's secure, but I'll just check it up again. Hopefully it's not. Just a second. I'll just get link. Anyone with link? Yes. Copy link, done. So I'm sharing the link again in the chat box. Open that, and that you'll be able to find all the resources. That whatever videos and all I'm making, that you'll be able to find. Did you
Ma'am,
open the
if
link?
you, now it's loading, ma'am. Is coming request access from college, ma'am. Wait, ma'am, 1 minute. Right, ma'am. Change mail ID.
Yeah, change your mail ID to Gmail ID. Okay. If you have a college email ID active, then I don't know about that.
Okay, ma'am. I change it, ma'am. Now it's came, ma'am.
Came right.
Yes.
So I'll put up my videos on YouTube.
Okay,
Okay.
ma'am. Okay. Okay, ma'am.
That also I'll send you a link right now. But I feel Yogesh, you're not able to follow anything right now, and until and unless you are looking at whatever we are telling you to look at, then you won't be able to understand unless you do that. Is that okay?
I can't understand, ma'am. Can you
No, I'm
repeat, ma'am?
saying ki until and unless you look at whatever material we are telling you to look at, you won't be able to understand it. Is that fine? Do you understand that?
No, ma'am.
See, just go through the material, go through the videos of Professor
Okay,
Arnab
ma'am. Okay,
Rao, Arnab Roy. Okay,
okay, ma'am.
NPTEL is sending you mails, right? That is how you get to know that, okay, these
No,
sessions
ma'am.
of
That's the invitation only is coming, ma'am. The behind the invitation is not coming.
behind the invitation of what?
Behind means like a material. If you are uploading any if any material is not coming, ma'am. Only NPTEL is that the time of meet will be 3 to 4 like that only it will come in, ma'am.
Ha, true, that is the mail that you're getting. Um,
Okay, ma'am.
do you get a mail like the material for week 3 has been uploaded?
No, ma'am. No, ma'am. No, ma'am.
Yes, you do. If you have enrolled for the course, you do.
No, ma'am.
I'm
It's not.
getting that.
I'm not getting, ma'am, that one.
Okay, I'm
That's
just
the that's the invitation only I getting, ma'am, from.
share your email ID. Oh, wait just a second. Let me just copy this link. Share your email ID with me, Logesh. I'll just forward you that mail. And if you're not getting it, then you have to take it up with NPTEL. Okay.
I shared, ma'am.
Okay. So there's another link I've sent you. Okay. So I'll just forward the whatever mail you're supposed to look at on your email ID. If you don't
Okay, ma'am.
understand that, write me a mail. Okay, or even ask
Oh,
if ask me to jump back on this Google Meet. Okay, this Google Meet is going to be active on this particular link. If you're going to ask me to come on this link, I will come and I will explain how to access all the different material clearly. Okay, if you're not able to understand where to get your CFD lectures from, then it's a very big issue. Okay, and whoever your professor is who's asking you to look at this material, just tell them also that if that this problem is existing, that you're not able to find the videos which you have to look at. And
oh,
if they want to talk to me, he can also write me a mail. Okay, my email ID I've already given to you on this chat, ae19d752 at the rate of smailiitm.ac.in. Okay.
ma'am, I have doubt, ma'am.
What?
Ma'am, if you have my ambition was aeronautical design, ma'am. Can you complete
Yes,
it after mechanical? What to study for aeronautical design, ma'am?
you will have to give your gate properly, and then you will have to apply for MTech, MS or PhD in some institute which has aerospace engineering. That is how you're supposed to go about with it. Okay, so your most
Now,
important thing is to complete your gate exam
okay.
properly.
Oh, okay, ma'am.
Okay, which year are you in?
Now I'm in final. My friend has came, ma'am. Now, he also registered, but for CFT, ma'am. But he's changed the course to renewable energy, ma'am. That's why I have problem, ma'am. None of them in my college took us
That's
here.
okay. None of them in your college is fine. You just need to like look at the online NPTEL mails. We'll help you out with those things. You do not need any classmates in general, and you can ask whoever is taking these NPTEL course with you also, right? The people who are attending these sessions with you, with Tul,
No,
Apurva,
ma'am.
and all that.
No, ma'am. No, nothing. No one is in my
But you can ask them, no? Online, you can ask them.
in online.
Just in the chat box, you ask them that can someone help me with this? And there is a forum also for
Where, ma'am?
NPTEL course.
Forum means what, ma'am? Forum means.
Just a second. I'll go to the course and I'll show you how it looks like. Share screen. Okay. So you've come to something like this. Can you see my screen right now? Wait a second.